Okay, so I'm going to talk about information design and robust predictions, thematically very closely related to what Emir talked about, which is quite nice. An overview of the talk. First, I'm going to give some background about why we would want to think about designing information, and then most of the talk is going to be about a certain incomplete information solution concept called Bayes correlated equilibrium. I'm going to talk about that as a tool for information design and providing robust predictions in games. And then the last third of the talk is going to be an application to first prize auctions. So obviously Stephen is on the hook here as well, so if you have really hard questions, I'm just going to dodge them and pass them to him. Okay, so information has been recognized as being an important factor in determining how people behave since at least the 60s. And game theory has been studying the role of information basically since that time. So a notable early example is Vickery's papers, which are the first to study Bayesian equilibria, first and second price auctions, were from the early 60s. So a qualitative difference between the way game theory approaches information and the rest of economics is that we're really concerned with the strategic effect of information. So, even if you were in a decision theoretic context, your preferences over alternatives would depend on what you believe about payoff relevant states of the world. But in a strategic setting, this is not good.
That was clear.
Yeah? I'll keep going from that point. Okay. This needs a light touch, I think. Okay. But in a strategic setting, your preferences over your alternatives also depend on what you think others are going to do, which is naturally going to lead you to care about what others believe about states of the world that are payoff relevant to them. Okay. But of course, others care about what you do. So you care about what others believe about the state of the world. You care about what others believe about what others believe about the state of the world. And you very quickly get to this infinite regress of players caring not just about the state itself, but on all higher order beliefs about the state. So it seems like this is going to make the analysis of games with information extremely complicated and cumbersome. But since Harsanyi, we've been using a tool to kind of cut through that infinite regress, which is the notion of a type space. So a type space is a compact way of representing all of that complicated interdependent information that players might have about payoff relevant states. So an interchangeable terminology that I'm probably going to slip back and forth between is referring to the model of information as an information structure. But here's what I mean by that. Rather than explicitly describing beliefs about the state, beliefs about others' beliefs about the state, etc., what we'll just talk about is that everyone has a type. Okay? And your type is a sufficient statistic for all that complicated information you might have. Every type is associated with a belief about a state of the world, theta, that could be payoff relevant when we add some actions in a payoff structure on top of this. But also you have a belief about others' types. Okay, so this T minus I is the set of all profiles of types of the other players in this economy. And together, the collection of the state, the types, and these belief functions are referred to as a type space. So from this object, you could derive that more primitive description of knowledge. If you take the marginal of this pi over theta, then you have what a type TI's belief is going to be about the payoff relevant state. And then from that you could progressively take marginals and compute what all of the higher order beliefs would be. Okay, so this is a well-established tool, and that's why I'm not going into too much detail, or why I'm going relatively quickly about it. So a ubiquitous assumption that we make in game theory, not always, but very frequently, is that these beliefs have additional structure on them. They're derived from some common starting point a prior pi that's a joint distribution over the state and everyone's types, and then a given types belief is going to be obtained just from Bayesian updating from this common prior. So you learn your own type, you know what the prior was over the state and everyone's types, and that allows you to form a posterior belief about the state and others' types. So the common prior is conceptually problematic, but also a very powerful tool. We could debate it, but that's not really the main subject of this talk. So for now, we're just going to assume the common prior. And then in the lecture on Sunday, we're actually going to come back to what happens if you don't have a common prior, which is the only reason for bringing it up at this point. Okay. All right. So the type space has been an extremely useful tool in game theory, and it's allowed us to analyze a wide variety of strategic situations. There are some very major exceptions to this rule, cheap talk being one of them, but I think it's fair to say that in classical game theory, a widespread practice was to take the type space as something that's an immutable part of the environment. We're just given a type space, we're given a description of information, and then we want to understand what are the implications of that information for strategic behavior in a particular game. And importantly, we're not talking about where the information comes from or what kinds of information we would expect to see in the world. Okay. Now, there are a lot of examples in game theory, and I'm going to give some examples later in the talk when we get to the application to the auction, where behavior can be very sensitive to the assumptions we make about information. So some examples of this, the coordinated attack game and Rubinstein's electronic mail game is probably one of the best examples, but also in these other settings, you change the information and behavior could change quite a bit. Right. So what that says is that we really care which is the right model of information. If we want to use these models to make predictions, we really want to zero in on those models of information that are going to be empirically relevant. Okay, but that begs the question is, which are the ones that are empirically relevant? In principle, you might try to go out in the world and just ask people, what do you believe? And Sylvain was talking about this in his lecture yesterday, that in principle you could go out and try to measure beliefs, but that seems like something that's it might be very difficult to do reliably and in a large-scale manner.
Sometimes you don't want to hear the answers.
Yeah, right. So I don't. Fair enough. Even if we agreed that we wanted to know the answer, then it's not even clear that it's practical to do so. Okay. So alternatively, what we could do is try to use theory and introspection to deduce what are the kinds of information that are likely to emerge in a world where people actually can influence the kind of information that they and other agents might have. And even if we can't get a very precise prediction for what the right information is, sort of second best alternative would be to at least understand in a broader way how our predictions of strategic behavior are sensitive to what we assume about information. Okay. So that's the very high-level motivation for why we would want to think about information and think about the information as something that might be designed or the result of premeditated calculation in game theory. So there are a bunch of recent approaches that have been employed in game theory for endogenizing information in games. So one of the literatures that we were talking about a little bit this morning is rational inattention, where you actually think of agents as choosing their own information, but subject to some costs or constraints on what they can learn about the environment. This is a very natural model. Another approach is the Bayesian persuasion model that Emir so eloquently exposited. So in this model, there's one particular agent, or it could be more than one agent in the model, who has a lot of information about those payoff relevant fundamentals and can use that knowledge and communicate that knowledge in a selective way in order to generate information for other agents in the model. Okay, and a typical assumption, as in the model we were discussing before, is that that Amir was discussing, is that this designer has their own motives. Okay, and they're going to design the information in order to suit their own interests. Okay, and there's a third motivation or style of analysis, which is the one that we're going to focus on in this lecture, which is that of robust predictions, and it relates to the sensitivity issue that I brought up on the previous slide. You know, maybe we don't really know who is designing the information or where the information came from, but we do know that we don't know what the information is. Okay? This is a known unknown. And we want to make a prediction for behavior in a particular game that's going to be safe, is not going to rely too much on particular assumptions about information. So rather than studying what behavior will look like for a particular model of information, we're going to look at the range of possible behaviors across some reasonable class of models of information. Okay. So I've formulated these as different paradigms, but really there's a close connection, especially between 2 and 3, the Bayesian persuasion and the robust predictions model, because you could think that this robust predictions objective could in many cases be identified with solving a family of Bayesian persuasion problems where we treat some kind of nature as a designer who anthropomorphizes our desire to understand what are the limits of behavior in some particular direction, in some particular direction in the welfare space, for example. So one case that we're going to talk about later in the lecture is, we might have a model of a game, and we want to kind of stress test that model. How far could how low could surplus go? How large could the surplus of a particular agent go? If it's an auction and we're concerned about expected revenue from the auction, how low could expected revenue go? And in that case, we're really solving a special case of this Bayesian persuasion model where, the direction in which we're trying to stress the model corresponds to the objective of the information designer. All right, so that's high-level motivation, and I'm going to get into some more specifics about how we're going to model robust predictions. So in addition to model of information that we had before, now we're going to say that this state is payoff relevant in a strategic interaction where there are n players, and each of these players has a set of actions that they could take. Player I's actions are AI, and these players have expected utility preferences that are represented by this utility index GI, and this is over the entire profile of actions taken by the players and the payoff relevant state. Okay, and we're going to assume as a baseline that there's some information structure, some type space, and at a minimum we think that the agents know the information that they would learn in this type space, but perhaps they know more. Okay, so that's the form of uncertainty about the information of the agents. Okay, so the standard solution concept that we're starting from is Bayes-Nash equilibrium. So if we have this basic game together with a model of information, now we have a Bayesian game where we could represent the strategies of the players as mappings from their types to distributions over actions that they could take in the game. And under a particular tuple of strategies, sigma, each player I has an expected payoff, which is just the expectation over realizations of the state and the player's types, weighted by the relative likelihoods of those pairs, and then also expectation over the actions taken by the players, which the distribution of which depends on the realized profile of types of this utility index. Okay, so this is all very standard, and a Bayes-Nash equilibrium is just a tuple of strategies so that no player wants to change their strategy. Okay, Okay. So as I was saying, you know, we want to capture the idea that there's some uncertainty about the kind of information that the agents have. So what we're going to do is assume that the agents have at least as much information as they would get in this particular type space, but possibly they have more information. So what does it mean to have more information? So suppose that we're given some type space T1 and T2. You know, each of these represents a separate and different, potentially different kind of information that the players could get about the state. So, you know, here we're getting types in some TI1s, and there's a pi1 distribution over types, and here correspondingly for the second type space. Then we can define a combination of two type spaces as being a larger type space where the agents get types which are ordered pairs, okay, of a type in each of those two type spaces that we started with.
Sorry, is that a union or a cross product?
It should be a cross product. It should be a product, actually. So the set of types in this larger space is the product of the set of types. That's right. Okay, good. Okay. And what we're going to require of this combined type space in order for it to be a combination of the two we started with is that, so a prior on this larger type space is going to be a distribution over the payoff relevant states, a type under this first type space and a type under the second type space. Okay. And what we want to be the case is that if we take the projection of that prior onto either the state and the first type or the state and the second type, then we get back the priors that we would have had under these type spaces. Okay. So, you know, why is this a combination? Well, you know, if you saw, suppose that you saw just the first coordinate of the type that you were going to get under this combined type space. If you conditioned on that type, Ti1, then you would have exactly the same beliefs about the state and T minus I1, the other player's first coordinates, as you would have had under this big T1. Okay, and the same goes for the second coordinate as well. Of course, the players may have additional information now because they learned both a Ti1 and a Ti2, and together those can have, those are going to tell you more about the state and about other types than you might have otherwise learned. Okay. So importantly here, we're only restricting the marginal distributions over these type spaces. And that means that the correlation between these two types, the two coordinates of the type, is a free variable. And as we vary that correlation, the players could get more or less information. Okay. But now we can describe what it means for one type space to have more information than another. A type space T prime is an expansion of a type space T if there's some other type space T double prime, so that this expansion is a combination of the type space T and T double prime. So basically we got T prime from T by combining it with another type space. Okay, and that other type space that we're combining with represents at a minimum the additional information that the players are getting. So if we want to know what are what is the range of behavior that could arise under different models of information that are at least as informative as a given T, then that's the same as saying what are the behaviors that could arise in Bayes-Nash equilibria under expansions of T, in the Bayesian games that we would obtain with a type space that's an expansion of T. All right? And that's our question. What are those behaviors? Is there anything meaningful we can say? So at a first cut, this seems like a very hard and probably intractable problem because this space of potential type spaces is very large. You know, we haven't even imposed any structure on the space that these types have to live in. You know, that's an endogenous object. In some sense, this problem is analogous to studying the range of behavior that you could partially implement through a mechanism in a mechanism design context under some indirect mechanism. Okay, so when we talk about partial implementation, a mechanism designer can freely choose the space of messages that the agents can send to the mechanism. And so the space of mechanisms that a designer could use is vast in the same sense that the set of expansions of a given type space is also vast. G is the utility index in the game, in the basic game in the background. Okay. And of course, we well know that the mechanism design problem, which looks very intractable when we work in the space of indirect mechanisms, becomes much simpler when you reduce the space of mechanisms that you have to consider. Okay, so a fundamental result in the theory of partial implementation is a revelation principle, which says that you don't have to use all of those mechanisms. In fact, you could restrict attention to a relatively small subset, and those are going to be sufficient to accomplish anything that you would want to do, and those are the direct mechanisms, okay, where agents just report their private information and then something happens as a result. So we can kind of normalize the space of messages that the players send to just being whatever their private information is. So it turns out that there is a similar tool in this information design robust predictions context, which is that if you want to know what could happen under type spaces that expand some given t, you don't have to look at all of those possible type spaces. There's a relatively low dimensional class of type spaces that you can use, and those are sufficient to generate all of the behaviors you might be interested in. Okay, so that's what we're going to talk about. Next is the revelation principle, if you will, for robust predictions. Yes?
How does this relate to communication equilibrium?
So it's closely related, and I'm going to talk about it in this bullet point. It's hidden right now. Okay, so you know, this isn't a new idea necessarily. Just one second. In the sense that, you know, similar ideas are at work in the notion of correlated equilibrium from complete information game theory, where, you know, you might ask, what are the range of behaviors that could occur in a complete information game as we vary the kind of coordination devices that the players have for their behavior, for correlating behavior. And correlated equilibrium is a solution concept that is itself endogenizing the role of information as a coordinator of behavior. Yeah?
Could you give an example of an operating game where the problem you described arises?
Yeah, I can, and I will towards the end of the talk with the auction. You know, here's a very trivial example, which relates to what we're going to talk about at the end. Suppose we had bidders who were competing in a first price auction, okay, and there's some value for the good, okay. And let's say that for the sake of simplicity, that all of the bidders have exactly the same value. It's a common value, okay. Now, if all of them knew what the value was exactly, then the analysis is trivial, right? They're just going to compete the price up to whatever that value is, right? So what's the behavior that we would see? We would see that everyone in the auction is bidding the same amount, and it's whatever the value is, okay? And here's another model of information, which is equally trivial. No one knows anything about the value. They have no information, okay? Then all these bidders care about is the ex-ante expectation of this value. And in this case, again, the Bertrand competition is going to force the bids up to exactly that ex-ante expected value. So, you know, the bidders are going to compete away all their rents either way, but behavior would look very different in those two cases. the distribution of bids and the distribution of the winning bid would look very different. So, if we were concerned about welfare outcomes, then we don't care about those two those two type spaces in particular. They don't generate different predictions. If we care about the distribution of bids, then the predictions are very different. And later on, I'm going to give other examples where welfare varies quite a bit depending on what we assume about information in that context. Okay, does that help?
Well, but what exactly is our goal to make some prediction regardless of what kind of information agents have?
The goal might be to predict what distributions of bids would arise in equilibrium.
Given any possible type of information that agents have.
Well, in general, I want to make such a prediction across some class of models of information. Here, we're focusing on models of information that are more informative than some baseline. That's the kind of sets of information structures that we're looking at. Does that make sense? Okay. Yeah.
Perhaps I missed, but here,
Uh-huh.
other types independent.
No, not necessarily. There's this pi, which describes the joint distribution of the state and the types, and it's some distribution. It could be correlated.
Independent are a special case here.
Absolutely.
And are players symmetric?
Not necessarily. No. No, they don't have to be. All right. So at any rate, the spirit of the exercise is very similar to what we're doing with correlated equilibrium, trying to make a set value prediction for behavior where we've kind of endogenized the role of information in the equilibrium concept. And the natural question you might ask is how you should extend, how you could extend correlated equilibrium to games with incomplete information. And there's a long literature on this subject, which I'm not going to review in detail. But here are some notable examples. Forge has a paper where she basically goes through a laundry list of possible definitions, some her own and some proposed by others, and contrasts the predictions that are made by those different solution concepts. I should point out that the idea of a revelation principle in information is also a mature idea, and it appears certainly in Meyerson's work. So I think what's novel here is, or what's novel in this more recent literature, is the idea that the information is, or the range of information models that we're looking at is really meant to capture what we don't know about exogenous features of the environment, rather than say, capturing the objective or what would be designed by some strategic information designer. So Meyerson's communication equilibrium, for example, has the spirit of, the players could set up an institution where they report what they know to some coordinator, and then the coordinator will take those reports and then use it to coordinate behavior of the players. Okay, but of course the players will only want to reveal what they know if it's in their own self-interest. So communication equilibrium of Forge or Meyerson has those extra constraints built in, which we're not going to talk about today. It's a superset of basically all of the other notions of incomplete information correlated equilibrium that are talked about in the literature. Well, no, I think in Meyerson's work he is using canonical information structures, but with extra restrictions. Okay. Yeah. All right. Okay, but the key difference, I would say, between all of these solution concepts and correlated equilibrium is that here we want to vary information not just about what others know, which we're already doing in correlated equilibrium, but also varying what these players know about these payoff relevant fundamentals. Okay, so here's the class of the solution concept that we're going to use. which is called Bayes correlated equilibrium. So a Bayes correlated equilibrium of this incomplete information game is simply a joint distribution over the set of states, the set of the type profiles of the players under this baseline information structure, and profiles of actions that the players can take in the game. Okay, so it's just a large joint distribution that satisfies a couple of conditions. The first is that if we integrate out the actions, we get back the prior over the state and the types that's part of the description of the baseline type space. Okay. And there's another condition, an obedience constraint, which is analogous to the obedience constraint in correlated equilibrium, which is that whenever a player has a type Ti and takes an action Ai according to this distribution, that player would actually prefer to play this action rather than switching to some other action. So the left-hand side of this inequality is the expected payoff that a player would get under the distribution phi when they get the type Ti and when they play the action Ai, the expectation of the utility index. On the right-hand side is the expectation if they switched from Ai to Ai prime. Okay, and what we're going to impose is that players don't want to switch. Yep?
What's the given AI on the right-hand side?
This?
Yeah.
So this phi is a joint distribution over states, type profiles, and action profiles. That action profile has an action for every one of the players. Okay. So yeah.
When you wrote the definition of baseline equilibrium,
Uh-huh.
in terms of sigmas, and that
Yes.
was conditioned on particular types,
It did condition on types. Those sigmas did condition on types. So it was a strategy that mapped from your type into, okay,
when you wrote something like this,
right. So this definition is suppressing strategies. There are no strategies in this definition, just like there aren't strategies in the definition of correlated equilibrium. Okay. So an interpretation here is that, and this is purely an interpretation, is that there's a mediator who knows what the state is and knows what are the types that the players would get under this type space. And this mediator can commit to a rule for making private recommendations to the players of actions that they should play. Okay. So if the mediator commits to using this rule phi, of course, the mediator isn't choosing the state and the types. He's just observing the state and the types and then sending these signals. And so whatever joint distribution over action recommendations that this mediator chooses, he has to respect this prior distribution. He doesn't get to choose the prior distribution over the state and the types. Okay. And what these constraints say is that if the mediator tells a player to take an action AI when they have a type Ti, the player's going to want to do it. Okay. They're going to find it in their interest to play AI rather than switching to some AI prime. Okay. Yep.
I'm wondering, where does the pi appear in the definition of the game?
Pi is part of this type space. Yeah, the part of the type space is a prior over the state and the types. So, there are multiple equivalent.
Okay, this prior is really type independent. Okay.
Yeah, there are multiple ways that I could have formulated this problem. We could have started with a prior over just the state and then talked about joint marginal or conditional distributions of types given states. But since we're not using that decomposition anywhere, it's convenient for this problem to just think of there being just one prior over the state and these types. Really we should think of these types as something that's kind of known to exist in the world. In the minds of this econometrician who's trying to make a prediction about behavior in this game, those types are known to be something that the players observe from, and they're drawn from a fixed probability law. Yeah?
So can we understand the first condition is simply that the prior of players about what the does have to be correct?
Yeah, that's right. Yes,
So we are fixing a common prior.
correct. Yes, I should have said that we're assuming common priors throughout the rest of this lecture.
And
Correct. Actions, types, and states. That's right. That's right. Okay. So we'll refer to these as obedience constraints.
And everybody knows this is
Uh, yeah, I mean, it's implicit in the definition of a correlated equilibrium that whenever a player forms, this conditional expectation of their payoff, they're using the same fee to form that conditional expectation. Precisely. All right. So these BCE are really the analog of direct mechanisms in the information design context, where here the normalization is that the information that players are getting just comes in the form of an action. You learn that there's an action that you should take. Okay? Not to be disrespectful to Stephen's ample naming skills, but another term that you might have used for this equilibrium that would evoke this connection is a direct equilibrium. Okay, this is an equilibrium that abstracts away from whatever intermediating information might be coordinating the player's behavior. Right. Okay, so here's the revelation principle for information design and robust predictions, if you will. So basically what we're going to argue is that if you want to learn about the behaviors that could arise under some expansion of this T in a Bayes-Nash equilibrium, then that's equivalent to looking at the range of behaviors that could arise under some Bayes correlated equilibrium. So what does it mean to say some behavior could arise under an expansion in some Bayes-Nash equilibrium? Well, if we have an expansion T prime of T and a Bayes-Nash equilibrium on this expanded type space, that's going to naturally induce a joint distribution over states, types, and actions, which we get just by integrating out the extra component in the type that comes from this expansion. So remember, the expansion is the combination of T and some other type space. So this little T prime is the extra component of your type that you get from the type space that you're combining with. And if we take the probability of, this is of a given state, a pair of types, this is a type in T and a type in the type space we're combining with, and then sum over the likelihoods of a given action profile. And if we take that sum over all of these added types, these combined types, then we're just going to get back this phi is the distribution that we would obtain. Okay, so that's what it means for an expansion T prime and a Bayes-Nash equilibrium to induce a distribution. So here's the theorem. A distribution phi is a Bayes correlated equilibrium of this game if and only if there's an expansion of T and a Bayes-Nash equilibrium of the expanded game that induces this phi. Okay. So what this says is if we want to understand the range of behaviors that arise under expansions, we just have to study the set of Bayes correlated equilibria. Okay. This is basically everything that I said. So let's try to prove this theorem. Correct. It's an if and only if. So let's first do the direction of showing that if we start with a Bayes correlated equilibrium, then we can find some expansion in some Bayes-Nash equilibrium that would induce this distribution. So you can't have anything that's a Bayes correlated equilibrium that couldn't arise in equilibrium from expanding the type space. Yeah?
Right question. So, can we think that the monitor first observes some signals from the players and then distribution should be generated?
So in general, no. And so this goes back to Vasiliki's question. There are two reasons why that might not be true. One is that it might be that this mediator in our model knows even more than the sum of what the players know under this baseline information. For example, we could assume that this T is degenerate. Players don't learn anything. You always have the same type, regardless of what the state is. Okay? But still, in this model, we're allowing for the possibility that this mediator conveys some information, positive information about the state. Okay. Another reason why you might not have that equivalence is, if the mediator is getting the information from the players themselves, well, then you have to wonder whether or not the players are actually going to want to reveal what they know to the mediator. You could lie about what you know and try to manipulate the institution. And there would have to be additional constraints to ensure the players don't want to do that. Of course, they couldn't want to do that in equilibrium. Okay, so why, was there another question? Okay. Why is a Bayes correlated equilibrium going to be in this robust prediction? Well, so if we start with a Bayes correlated equilibrium phi, we could always define our expansion to be your original type and the action that you would draw under this phi. Okay, so in effect, your type corresponds to whatever your base type would be and whatever you would end up doing under the distribution. So this is this pi prime. The prior that we have under the expanded type space is just phi. Okay. And then we're going to construct an equilibrium of this expanded type space, and it's just going to be well, I suppose it's not an identity; it's more of a projection that you play the action component of your type with probability 1. Okay. So that's our proposal for an expansion and an equilibrium to induce this phi, and let's verify that actually this is a Bayes-Nash equilibrium. So some notation, we'll just write phi sub I for the marginal distribution of phi on player i's type and player i's action. Okay. So it's important to remember that these actions on the left and the right-hand sides here are actually, they mean different things. This one is a type. This is a component of the type. This one is the action that this player takes in the game. Okay. But what we're saying is that, first of all, we're choosing the same space, the same set to represent both types and actions, and that you play the action that's part of your type under this strategy. Okay, so why is this going to be an equilibrium? Well, incentive compatibility is just going to follow from the obedience constraint on the correlated equilibrium. So suppose that you're player I and you want to deviate to some other strategy, sigma I prime. Okay, so sigma I prime is going to say to do something other than AI sometimes. So there's positive probability that you play AI prime when, even though your type says to play AI. Okay, and then you're going to get some other payoff here. And there should be a sum actually over AI primes. Apologize for that. Okay. In any event, if you sum over all of the AI primes, well, we could break that sum into two pieces. First summing over all of the types that this player I has, and then given player I's type, integrating over the types of the others. And if we do that, then we're basically going to get the expectation from player I's point of view of the conditional expectation of his payoff when he has a type Ti and he draws an action AI. Okay? And by assumption, the payoff from playing AI prime if you drew AI is less than the payoff from playing AI when you drew AI. And then this is what you would get actually if you followed this strategy of always playing the action in your type with probability 1. So the summation over here is a little wonky. I will correct the slides before they get posted. Okay, so that's why, that's going to be a Bayes-Nash equilibrium and an expansion that induces this Bayes correlated equilibrium. So in the other direction, we start with an expansion and a Bayes-Nash equilibrium, and we want to argue that the joint distribution over types, states, types, and actions that's induced is going to be a Bayes correlated equilibrium. And that comes from just the incentive constraints for equilibrium, where we sum across the expanded types that that the player could get. So, okay, we have an expansion. That means that players' types are going to be their original types and some extra dimension of your type, T prime. Okay, so we're going to define the induced distribution just by summing across all of those additional dimensions. of the type. Okay. Now, suppose that there was some type and recommended action under which a player would prefer to deviate to some AI prime rather than playing AI. Okay, well then what's going to go wrong? We could consider an alternative strategy where this player, instead of playing AI, whenever this player would have played AI, and whenever their type is TI, switch to playing AI prime. Okay. So this is a well-defined alternative strategy that this player could have adopted. Whenever the original strategy said to play AI, when your type was TI, play AI prime instead. Okay, the difference in this player's payoff from this deviation is just going to be an expectation of the change in your payoff from switching from AI to AI prime on those events when you would have played AI under the original equilibrium strategy. Okay? And this is simply the probability that you would have, this should be actually the reciprocal. So this is just the total probability that you get this type and this action times the conditional difference in payoffs from playing AI prime and playing AI. Okay? And that's positive. So if you would want to deviate from the base correlated equilibrium, then you'd have positive gains from deviating to this sigma I prime. But that contradicts the hypothesis that we started with strategies that were in equilibrium. Okay. So another way of formulating this is, if we have some type space and some equilibrium strategies, then whatever type players get, there's some action that they play in equilibrium, and that's a best response. Now suppose you tell that player, you don't know what your type was, but I will tell you that under this, for whatever type you would have gotten, this AI is the action that you would have played. Okay. And the question is, would the player want to take that action if this was the only information they had? And the answer is yes, because you know that whatever the type could have been that would have given rise to this action, you couldn't do anything better. So in the aggregate, across all of the types that could have given rise to this action, you can't do better either. Right? And that's basically the logic underlying this equivalence. Okay. So that's the general result that I want to talk about, is this revelation principle. There's a lot more that I could say, but I won't. Just a brief overview of additional topics in this literature. You could talk about comparative statics. What are the kinds of changes in information that are going to lead to smaller or larger predictions for the set of base correlated equilibria? And then, we could also sort of compare this solution concept with other solution concepts that are in the literature, like communication equilibrium. Cotter has a definition, which is basically correlated equilibrium in the strategic normal form of the game. So there's correlation in the strategies that players use, but this correlation doesn't tell you anything about the state itself. It's independent of the state. There's a recent paper by Mateve and Perego and Taneva, which is trying to bridge the identify the relationship between Bayesian persuasion methodologies like concavification and this base correlated equilibrium approach. Yeah, so it's there. It's not I think it doesn't end up being as powerful a tool in this context as it does in Bayesian persuasion. And the issue is precisely this dimensionality issue, that the space that you end up having to concavify over becomes very large, like the universal type space. But anyway, there is a conceptual link there. And everything that we were talking about was for finite games, but one can in principle extend it to infinite games. Okay. So I think this is, there is also literature following Stephen and Dirk's papers, a lot of which is Stephen and Dirk and co-authors, of whom I am one, on applying the solution concept and trying to learn something about Bayesian games in an information-free manner. Okay. So here's a list of applications, and this is the one that I want to talk about in practice. Yeah, today.
For the previous result, the fact that in some expansion there might be like a redundant type, another type using the same hierarchy belief that the original.
Not really, and in fact, it's essential. It's it's by design. I guess it depends on what you mean by redundant types.
Like
One.
two different type spaces, two types using the same hierarchy of belief.
Good. Okay, so that is. So think about what the specialization would be of this solution concept on a complete information game. We could always embed a complete information game in this context by just having there be a single state. Okay. This solution concept is going to reduce, and then everyone has the same higher order beliefs, of course, which just puts probability 1 on this particular state, and there's common certainty that that's the state. Then this solution concept just reduces to correlated equilibrium. So I think you're right that, or something related to what you were asking is that this solution concept is doing two things simultaneously. One is varying what the players know about the state, but also varying what they know about what others know in the sense of providing the players with correlation devices. And, you might say that one conceptual weakness here is that we're varying both simultaneously. Maybe you'd want to vary one without the other. It's not entirely obvious how you would separate those two. Okay. Does that answer your question? Okay. All right. All right, so let's talk about how you might actually use this in practice. So I think this is... this is a potentially fertile area for new research, and especially for graduate students who are looking for interesting problems to work on. Sort of revisiting classic results in game theory and trying to understand how those results are sensitive to what we assume about information is kind of a wide open topic. There are some interesting preliminary results on it, but the methodology hasn't been applied widely yet. So here's one such application. There are n bidders for a single unit of a good, and as we were saying before, all of these bidders have exactly the same value for this good, and it's drawn from some cumulative distribution f, and this has support on some interval. Let's assume for simplicity that it has a density, and that density is positive on that interval. Not because these are essential assumptions, but just to make our lives a little easier. Okay, so these guys are going to, and gals, are going to play a first price auction, meaning that they submit bids, which are non-negative real numbers, and the winner is chosen randomly from the set of high bidders, so we're going to break ties uniformly, and that winner gets allocated the good and has to pay an amount to the seller which is equal to the bid, to the high bid. Okay, so just the usual definition of first price auction. In order to relate this to the earlier model, the state here is just this value that summarizes all of the payoff relevant, that's a sufficient statistic for all the payoffs in the game. And we're going to assume actually that the players don't know anything as a baseline. Okay, so they all get exactly one. It might be that they all have exactly the same type. Okay, so they don't, in which case the players wouldn't know anything about the value. Now there's no reserve price in this auction, okay, and everyone bids a non-negative amount. So that basically means that the good is always allocated to someone. So, and the fact that there's a common value means that from a welfare point of view, it doesn't matter who the good goes to, okay? The outcome is efficient as long as someone gets the good because these buyers value it more than the seller. So total surplus is always going to be V hat, which is just the expectation of the value. So in terms of welfare outcomes that we might be interested in this context, it's how that surplus is going to be split between the bidders and the seller. Okay, the seller is going to get some revenue, and then total surplus minus that revenue is going to be the sum of the surpluses of the bidders. So our robust prediction question is going to be, what are the possible splits of that surplus that could arise under some model of information? Okay. We know that this auction is happening. We know something about the distribution of the value. We don't know what kind of information the bidders have. What are the things that we can say that just rest on the assumption of some common prior and equilibrium behavior? Okay. So here's the example that I was giving before. What would happen if they had symmetric information? So suppose that all these guys have the same set of possible types, guys and gals have the same set of possible types, and with probability 1, they all have the same type. Okay, that's what this says. So here I'm just decomposing that prior into, we already have a distribution over the value, and then conditional on the value, there's some probability of getting a profile of types. And here what we're saying is that a given profile of types has positive probability only if everyone has exactly the same type. Okay, so what this means is that if you have a type, Ti, everyone else had exactly the same type. And actually there's a common expectation of the value, which is just the expectation of the value conditional on getting a type Ti. So all the bidders have the same, think the good is worth the same amount, and they're just going to compete away all their rents. And the seller's going to get everything. Okay? And that's going to happen as long as the information is symmetric. So what that tells us is that maximum revenue is just total surplus. It could be that the bidders compete away all their rents. So our robust prediction is not really so interesting on the maximum revenue side. The minimum revenue side is a little more interesting. So, in principle, it could be that all equilibria under all information structures result in the seller taking all of the surplus. But we know that's not going to be the case. So here's a simple example where the bidders don't compete away all their rents. And this is a proprietary information model of Engelbrecht, Wiggins, Milgram, and Weber. So in this model, bidder 1 is informed, meaning that bidder 1 is going to see the value. Exactly. Whatever the value is, bidder 1 gets to see it. And the other bidders don't get to see anything. So bidder 1 has a big advantage. That's what I mean here, that these other bidders, they only have a single type. And with probability 1, the type of the first bidder is equal to the value. Okay. So it turns out that there's an equilibrium in which the informed bidder bids this beta of V. Is a monotonic pure strategy. And that bid is the expectation of a random variable W drawn from the same F as the value, conditional on that W being less than or equal to V. So in other words, bidder 1 bids the expectation of the value conditional on it being less than its true value. Okay? And the uninformed bidders, what they do in this equilibrium is, they don't know anything about the value. One way of describing their strategy, they're going to play mixed strategies, and one way of describing that is they simulate observations of the value, which of course isn't really related to the value in any way, but they simulate these draw random variables Si, so that this should be an n-1 actually. So basically, the distribution of these signals is equal to f to the 1 over n-1. Okay, why is this the correct distribution? This is so that the distribution of the highest signal of these uninformed players has the same distribution as the value, as f, right? So the max of S2 up to Sn has a distribution which is the same as the value. And then whatever signals they draw, they just bid according to the same beta. Okay. So what this equilibrium looks like, it looks like actually there are two bidders. Okay. There's one bidder who's informed and bids the expectation of the value conditional on it being below its true value. And then all of the uninformed bidders collectively behave as a single bidder who also gets an independent draw from this F and bids the same amount. Okay? So it turns out this is an equilibrium. I think for time constraints, I'm not going to go into detail exactly why this is an equilibrium. But I do want to say a couple of things. Okay. So if you know, or if you've studied Bayes-Nash equilibria of first price auctions in the independent private value model, then it's easy to deduce from that equilibrium why this should be an equilibrium. Okay, so why is that? Think about a model with two bidders who get independent values drawn from F. Okay, that model looks the same for bidder 1 as this model. Okay, because this beta is exactly the form of the bidding function in the independent private value first price auction. In general, the equilibrium of the IPV first price auction is everyone bids the expectation of the highest of the other's values, conditional on it being less than their own value, okay? Which is exactly what this informed bidder is doing. So that allows us to immediately conclude that this is an optimal strategy for the informed bidder, okay? Because for the informed bidder, his signal is his value, right? The uninformed bidders, actually, it's not immediately obvious that their strategies are optimal, but actually it is. So let me explain why that's the case, briefly. So suppose that you have an uninformed bidder who doesn't know anything about the value, but bids some beta of V, okay? So two things have to happen in order for this bidder to win. The first is they have to outbid all of the other uninformed bidders. Okay? There's some probability that happens, but it doesn't tell them anything about the value, right? Because the other uninformed bidders' bids are independent of the value. So let's think about what the surplus would be of this uninformed bidder conditional on outbidding the other uninformed bidders. Okay? Well, then something else has to happen. You also have to outbid the informed bidder, right? And if you bid beta V, when are you going to outbid the informed bidder? You're going to outbid him whenever the informed bidder's signal was some W less than V, right? So basically, if you bid beta V as an uninformed bidder, you're going to win whenever the true value was less than V. Your surplus on that event is just the expectation of the true value, conditional on it being less than V, which is exactly what you're bidding. So in other words, no matter what these uninformed guys bid, the expectation of the value conditional on winning is their bid. So they're going to get zero surplus. So actually these uninformed bidders are going to get zero surplus no matter what they bid, and they're willing to randomize in this manner. Okay. Now the bottom line is that revenue in this case we know is going to be the expectation of it's going to be the expectation of the highest of two draws from beta times a beta of a signal drawn from F. But there's a revenue equivalence theorem in the independent private value model, and we know that revenue from a first price auction is going to be the same as revenue from a second price auction, which tells us that revenue is just going to be the expectation of the second highest of two draws from F, which is less than the total surplus. So the bottom line is that in this model, the bidders do get some information, in particular the informed bidder gets some positive rents, and the seller doesn't get all the surplus. So all of this is a somewhat elaborate illustration of the fact that predictions for surplus are going to depend on what we assume about information, and there is non-trivial variation in welfare outcomes across different models. So this begs the question of what is minimum revenue? What is the lowest that revenue could go? Maybe it's zero. It can't be zero. It can't be zero. It's got to be strictly positive. Why is that? Well, the only way, what would everyone have to be bidding if revenue was zero? Zero, right? They have to bid a non-negative amount. So the only way that revenue could be zero is everyone bids zero all the time, but that can't be an equilibrium, right? Because then everyone is tying, and they're all equally likely to win the tie break, so you win with probability 1 over n. But you could just bid an epsilon and win all the time, right? With tiny cost. So bidding zero is not going to be an equilibrium, so there's some non-trivial lower bound, and we want to know what that is, and we're going to try to identify it by studying minimum revenue across Bayes correlated equilibria of the first price auction. Yeah?
You could still, at least in theory, have, and even though every equilibrium gives you strictly positive surplus at the end, you could just have all these things here.
You could. But you know, there's got to be some bidder who wins with probability less than 1 over n. You know, it can't be that everyone wins with probability greater than 1 over n. So if revenue was too low, it would mean that bidder surplus is, it would mean that, you know, with high probability, the winning bid is very low. There's going to be someone who can bid, who could increase, well, okay, let me not get into this. Stephen's right. It doesn't happen. And the proof of why it doesn't happen is in the proof of the result. So maybe we'll come back to it. All right. So we want to use Bayes correlated equilibrium. I had to speed up a little bit because I'm going to, well, this talk may spill over a little bit into the next lecture. So one of the reasons that this Bayes correlated equilibrium is a tractable solution concept is because, you know, like correlated equilibrium, it's a set of probability distributions, and they're described by these linear incentive constraints. Those obedience constraints are linear. And so in general, you know, that's a nicely behaved geometric object, the set of Bayes correlated equilibria. It's a very high dimensional object, you know, especially in a game where you have infinitely many types and actions. You know, even as we tried to approximate it with a discrete game, you know, it's going to be high dimensional. So it's really impractical to try and completely characterize the whole set of Bayes correlated equilibrium beyond toy examples. But it's going to become much more tractable, first of all, as we really are only studying the projection of the set of Bayes correlated equilibrium into a low dimensional space, namely the set of expected revenues that could occur. But also, you know, one of the nice things about Bayes correlated equilibrium is that it's very easy to solve numerically. Okay, so one thing, and basically how we solved this problem of finding minimum revenue in the first price auction was to solve examples numerically. Okay, and what those numerical solutions told us is what the pattern, you know, which of these constraints matter. So there are lots and lots of constraints that are defining the set of Bayes correlated equilibrium. At any given extreme point, not all of them are going to be critical, not all of them are going to bind. If you know which are the critical constraints, that tells you a lot about the structure of the solution and could help you to characterize it. So what we did was we went back and forth between simulation and theory in order to sort of guess and verify which are the right constraints for pinning down minimum revenue. The reason I'm talking about this is, you know, I have a general view that we don't talk enough about how the sausage is made. You know, everyone wants their result to look really clean and crisp at the end, but often they didn't get there that way. And if, you know, one wants examples to emulate of how to actually analyze a model and obtain those results, sometimes you do have to talk about the more gruesome aspects of the process. That was the sausage analogy. Okay, so what I want to actually do is look at a simulation of this model with you guys. So I should add a caveat that this is not actually how we solved this model. We solved this, we arrived at this solution by studying a very different auction design problem, and through, you know, a very convoluted sequence of steps, we're able to arrive at this one. But I can kind of cut to the chase and try to solve this problem numerically as if we started with this exact formulation of the problem. So this tool that I've just put up is a tool that we wrote for basically setting up the linear program of solving for correlated equilibria and then exploring the solution. Okay, and what I've done is input into the program a first price auction, a discretized first price auction where each of the bidders gets 30 bids and there are 30 possible values. Actually, I think I wanted to set it up slightly differently. The grid of values is going to be between 0 and a half. Bids, excuse me. So in this discretization, you can't bid more than a half. Okay. Now you put that into the number cruncher and it solves it pretty quickly. but I've clearly done something wrong because it shouldn't look like this. Ah.
What's the distribution of values?
Uniform between 0 and 1. Minus 1. There we go. Okay. So this tool is going to help us understand features of the solution. So the linear program solver solved the discretized version of the auction. Over here, it's just plotting what the outcome was in player's utility space. And I'm not quite sure why it's giving me this incorrect number, but really it's actually about a sixth. Oh, here we go. It's about 1/6 for each of the players. So each of the players in this solution gets 1/6, which, rounds to 0.17. In this panel, it's uniform on 0, 1. Yeah, that's the distribution of values that we're using. So in this panel over here, what we're plotting is the joint distribution of the player's actions conditional on the state. Okay, so the states are increasing in the value. So this state of 0 is the lowest value. And what it says is when the value is the lowest, the players bid 0, basically. Now, as I increase the state, we can see how the joint distribution of the actions changes. So I'm increasing the value. Now let me interpret this for you. What this is saying is that as the value increases, the bids are increasing in a kind of monotonic fashion. And what it says is that on this, the support of bids has the feature that the maximum bid is constant. Okay, someone is always bidding this amount. Either it's bidder 1 or over here it's bidder 2. Okay. So what this says is that as the value increases, the maximum bid is increasing monotonically. Okay. So in other words, the bids are basically the signals that the players are getting in this Bayes correlated equilibrium. So what it says is that the maximum of the two players' signals is revealing the value. Okay. Okay, so that's one interesting and useful fact. I can tweak this program. So now it's showing the joint distribution unconditional on the state. And if we go to a log scale, it's a little bit easier to see. So this is the support. It's actually going up to about 1/3. Okay. Now you can't tell from this picture, but actually this joint distribution is independent. Okay, so I can't see that directly within this program. But if you took this marginal distribution over bids, you would find that it's an independent distribution. So what that tells you is that also at the solution, the joint distribution of the signals, unconditional on the value, is independent. Okay. And there's another useful fact which I want to exposit using this tool. And that's exactly which are the critical incentive constraints. Okay, which are the obedience constraints that are binding at this revenue minimizing Bayes correlated equilibrium. So this panel down here is showing what a player's payoff is as a function of the action that they were recommended to take by the mediator and the action they deviate to. So in this example, this player was told to bid 0 by the mediator. They got a signal that corresponded to a bid of 0. And as they deviated to other possible bids, well, obviously they can't do any better. So this has to be weakly decreasing. But in fact, it's flat for a while, and then it decreases. Okay. Now, I could increase the bid that the player is recommended to take. So what I'm doing is moving the recommended action to the right. And you notice that, the gray color is highlighting which of those constraints are binding. Which of the ones you are indifferent to deviating to. This player is indifferent to deviating to. And basically what this computation is telling us is that for any recommended bid, the players are going to be indifferent between that bid and all of the higher bids. Okay, so lots and lots of these obedience constraints, incentive constraints are binding, and they all go up, and they all go exactly to the same upper bound. Okay, so these are all features of the critical information in Bayes correlated equilibrium that minimizes revenue. Okay. We'll stop. Okay. So that's, I think that's, yeah, okay. So those are basically stylized facts that we can glean from this program. And now I want to try to use them in order to analytically solve this problem. Okay. Now the first step, I would say, is to just describe what we see.
Can I just ask one thing about that
Yeah.
previous list? It seems surprising that they're independent signals. You might have thought before you get the actual numerical solution that somehow negative correlation in the signals might be a good thing because it gives more information rents. Can you tell me what's wrong with my intuition that you might want to have negatively correlated beliefs about the value between the two bidders?
It's a good question. I honestly don't really know how to think about information rents in a precise way in a world outside independent signals. I mean, I guess...
Information rent was a loaded word because it has kind of overly precise meaning, but
Yeah, I think the independence is hard to I find it hard to motivate from first principles. It kind of pops out. It doesn't, strictly speaking, have to be independent if you go beyond two players, which is a somewhat subtle point that I'm not going to make today. The honest answer is that I don't know. It might be that, you know, there's not a great motivation for it. It just kind of pops out of the rest of the constraints of the model. The other features, I think, have more solid primitive motivations. You know, why should we think that upward, well, not these necessarily, but certainly this one, you know, why should we think that upward constraints are the critical one? Well, that goes back to the earlier motivation about why revenue can't be zero. If the distribution of bids is too low, if it's compressed around zero, then someone could deviate up, and the increase in the probability of winning is going to be very large relative to the additional amount that you have to pay. So that sort of suggests that upward deviations are the ones that are going to constrain things.
If signals are negatively correlated and I receive a low signal, that means that I know that you must be receiving a high signal, so that's going to induce me to bid higher.
right. But there's a limit to
Yeah.
how negatively correlated they can be because of this. So we can't have them. The more information we have, the less negatively correlated we get. But we could still have negative correlation in the belief about the value.
But I'm not sure why negative correlation will contribute to low revenue.
Right. I think Eric's point is if you had different values, and if values were negatively correlated, you might think that that would reduce competition. But here, everyone has the same value, right? And it's not obvious that your expectation of the value is, is monotonic in your signal. Okay.
Yeah. So it's hard to get negative correlation in the expectation of the values across players. Once
You could do that too, and I think that's probably the right way to formulate your question: is why don't you have a structure that induces negative correlation in the expectation?
Then maybe you
Yeah.
can't.
Yeah. I doubt that. But yeah.
These stylized facts, you actually prove them theoretically, or they're just derived from linear?
No. There's a proof. And so let me be clear. That numerical exercise was not intended to be a proof. That was motivation. Okay, that was motivation for a guess and verify strategy. It says, let's try to identify essential features of the solution to this problem and then use those to analytically characterize the solution. Okay. So I want to speed up a little bit because I don't want to give myself too much of a deficit for the next lecture. Okay. At a very first cut, let's just try to construct what the information equilibrium seems to be that is the worst case. Okay, so remember we wanted the signals to be independent, first of all, and we want the maximum of the signals to reveal the value. Okay? And there's a natural way to do that. Let's construct information where these bidders do get independent signals that are all draws from f. This is the f that's the distribution of the value, but to the nth root. Okay? now the distribution of the maximum of these signals is going to have a distribution which is f, the same as the value, right?
So you're
And-
not generalizing from the uniform distribution.
I'm now generalizing from the uniform distribution, exactly. So we haven't looked at non-uniform simulations. We're hoping against hope that these stylized facts are not special to that computation, and that'll be vindicated. Right. And then we correlate these signals with the value by just making sure that the value is always the maximum of the signals. Okay, so that accomplishes 2 of our stylized facts. This is an equivalent interpretation, but don't worry about it. Okay. So we're going to let G denote the distribution of the highest of n minus 1 draws. So from the perspective of any one of these bidders, this G is the distribution of the highest of the other bidders' signals. Okay? And it has an associated density. So what we're going to do, the other criteria, one of the other criteria that we had was that the bidders use monotonic pure strategies. The bids were supposed to be sort of 1 for 1 increasing in these signals. It turns out that this function is going to be a monotonic pure strategy symmetric equilibrium of the first price auction under this model of information. You bid the expectation of a random variable drawn from this G conditional on it being less than your signal. Right. Now why is that going to be an equilibrium? Let's try and argue why this is an equilibrium. So suppose you're a bidder, you have a signal S, and in equilibrium you're supposed to bid this beta lower bar of S, okay, but you think about deviating to some beta lower bar of S prime where S prime is smaller. So you're going to bid as if you had gotten a smaller signal. I want to argue that that's not a good idea. You're not going to want to do that. So why is that? Well, you're going to win whenever the others bid less than beta lower bar of S prime, all of the others do, which is when the maximum of the other signals is less than S prime. So this is the probability that you win if you deviate in this manner. Now importantly, if you win, other signals are less than S prime, which is less than S. So you had the highest signal. Okay? If you win with a bid lower than your equilibrium bid, you only win when you had the highest signal. And under this model of information, the value is equal to the highest signal, which is yours. Okay, so you know that the value when you win is just your signal, and you're going to have to pay this amount, beta lower bar of S prime. Okay? Now, basically, this is exactly, again, the independent private value surplus, as if the bidders just had private values that were independent draws from F. Okay? Your payoff when you win from getting the good is your signal, and you're bidding the expectation of the highest of the other signals conditional on it being less than your own. Immediately we can conclude that you can't profitably deviate downwards. Okay. What about going up? Okay, if you try to deviate, this should be a beta lower bar here. If you try to deviate and bid as someone who got a higher signal, then well, the events where you are going to win is when the highest of the others signals is, between the lower bound and this S prime. Now, sometimes you're not going to have the highest signal, which is exactly when others' signals were higher than S. So your value, if you win, is going to be the maximum of your signal and the highest of the others' signals, where that highest has this density G. And then, on the event that you win, you're going to pay this beta lower bar. Now, you can just substitute in what this beta lower bar is, and you're going to get this expression, right? Because beta lower bar is just the expectation of a random variable drawn from G, conditional on it being less than S prime. And basically, the terms, the integrand in here is 0 whenever the highest of the other signals is bigger than your signal. So the reason why that's important is because the surplus from deviating to a higher bid doesn't depend on the type that you pretend to be. It doesn't depend on the S prime. It just drops out altogether. So your surplus is constant. If you're going to deviate to a higher bid, it doesn't matter which one you deviate to, as long as it's within the support of equilibrium bids. And what that tells you is that the player's surplus is constant as they deviate upwards. So of course you wouldn't want to deviate, or you don't have a strict incentive to deviate. Okay. And incidentally, now we've verified the last of those stylized facts, which is this upward indifference. All of the bidders are indifferent between their equilibrium strategies and any higher bid. Okay. And here's the specialization to the uniform case, which I won't dwell on. Okay. So that's just a construction that happens to fit the stylized facts that we inferred from that simulation. The question is why? Can we prove that this is actually the Bayes correlated equilibrium that minimizes revenue? And we're going to do that. And the way we're going to do it is an indirect argument. We're going to derive a lower bound on revenue and show that this equilibrium attains that lower bound. That lower bound is going to come from ignoring all of the constraints except the ones that we think matter, namely those constraints corresponding to deviations to higher bids. Okay. We're also going to simplify the problem by not looking at all of the Bayes correlated equilibrium, but just a particular marginal of the equilibrium, which is the distributions of winning bids, of the highest bids that could arise in equilibrium. Okay, and it turns out that this is going to be a tractable way to analyze how low revenue. Now, obviously, if you know what the distribution of the winning bid is, you know what expected revenue is. So if we find lower bound on expected revenue across these winning bid distributions, that'll give us a lower bound across Bayes correlated equilibrium as well. So this curly H is the set of distributions of winning bids that could arise in some equilibrium. And it contains, for example, any distribution that has F as a mean preserving spread that's coming from symmetric information. It contains the distribution that we got in the Engelbrecht-Wiggins example, and it contains this H lower bar, which is what I'll call the distribution of winning bids that arose in the construction we just did. Okay. And of course, we're going to argue that this H lower bar has lower expected revenue than any other element of script H. Okay. I only have a couple minutes left, but I'm going to crack on, and we'll see how far we get, and then we'll pick up at the beginning of the next lecture. Okay, so actually we're going to prove something even stronger. All we wanted to prove was that this H lower bar has a lower expectation than any other element of script H. What we're going to prove is that it's actually lower in the first order stochastic dominance ordering than any other element of H, which is kind of surprising. So the stochastic dominance order, H dominates H prime if the CDF is lower at every point, which means that H puts more probability mass on higher realizations than H prime. And an equivalent characterization is that for all monotonic functions, this should be H and H prime. The expectation of a monotonic function under H is greater than that under H prime. And this is a partial order, only a partial order on probability distributions, which again is part of the reason why it's surprising that we can prove that there is a minimal element in this ordering within this curly H. So here's the main theorem that we want to prove. There is a minimal element of this set of winning bid distributions in the first order stochastic dominance ordering, and it's the one that we constructed. Okay?
So it says a minimum element and it says this minimum element. So there's a switch in uniqueness between the first and the second.
I could have said H lower bar is the minimal element of H.
The minimal.
Yeah.
But there's only one then.
Yes.
Okay. It just says there exists a minimum.
Good. So I should have written this differently. I should have said H lower bar is first order stochastically dominated by any other H in curly H.
You mean just the minimum? Not
Yeah, it is the minimum. It is the minimum. Correct. Good. I'll stop there. So, see you all on Sunday.
Thank you.
Suspense.
All right. Yeah.